Good morning, everyone. My name is Ray Bell. I'm with Atheros, and I'm here with one of my colleagues, Dr. David Rieken, who will come up in a moment with me on the stage. But what we want to talk to you about today is AMI 2.0, driving decisions at the edge. Today's topic will discuss combining open standards, embedded edge computing with the emerging LTE infrastructure to deliver maximum value for AMI 2.0 and beyond. As I mentioned, my name is Ray Bell, and Dr. Rieken here, who is the VP of Research at Hubble, will follow me after I give a brief introduction. And Dave will actually provide you a lot more technical information and valuable information about his work at Hubble. AMI has now evolved from a focused revenue use case to a multi-sensor platform. We talked about that yesterday. And using this new platform, it enables the utility many efficiencies in the management and control of their next generation grid. So what is AMI 2.0? Well, in 2004, when I got involved in this industry, the use case was to move from mechanical meters to digital meters and to report data on a daily basis to the head end. And the requirement was to provide this information to the consumer so they could understand the impact of time of use on their bill. So the real use case was to deliver that revenue meter data, provide service and load control functionality, report on some local power quality at the service point, and outage event and device management events. Today, 20 years later, a lot's changed. We have the electrification of the automobile industry. We have the improvement of renewables. They're now on solar is going on almost every home in America. We have advances in battery storage technology. Tesla's been a pioneer to help us drive that technology into the home. We have smart appliances that are now talking with each other, looking to interact with the grid. So AMI has actually expanded from simple meter reading to having to interface with all these other aspects of energy consumption at the grid, at the edge. So what does this mean? It means that what you really need in AMI 2.0 is a computer, an open standards-based computer at the edge. A computer that you can actually, the ecosystem or the utility can develop applications that might look for fault detection, that might look for transformer protection. We demonstrated that yesterday. We'll be showing that later on today. If you haven't seen that, come visit us. And so you want to actually add the ability to have autonomous control, local decisions at the edge of the network. You also want to have semi-autonomous control, so that application that's running in the meter can get market signals, utility signals, make decisions locally, report back those decisions to the network. Now, if you look at that, there's also a movement in the industry to look at building a digital representation of your network. And this digital representation can be used to drive many efficiencies in the operation of your grid as well as the improvement and lowering of your line losses, your physical line losses, etc. So what's a twin? A twin is really an up-to-date representation of an asset in operation. Now that asset could be your meter, it could be the transformer above your meters, it could be the circuit that those meters are on, it could be the substation, the zone substation, or it could be the grid itself. So and really that component is driven by sensor measurement and operating conditions. So that data is going into this twin, which is in your data center, and then you can actually make intelligent decisions about, you can actually see things like a cracked insulator or your phase imbalance or things that actually really impact your business. You can, if you have to roll a truck, you can understand the health of your other equipment on the circuit. And so when you're out there and you've moved that truck out there, your lineman can actually address the other part before it breaks as well. So this gives you visibility. It's like, if AMI was watching a movie in 280p, AMI 1.0, AMI 2.0 is like watching the movie in 8K. Today, when we first started working with these digital smart meters back in 2003, they were recording data. The average recording, we were getting 30-minute intervals. That's what people wanted. Demand register reads once a day or once at midnight. Pretty basic stuff. Today's meter, today's 2.0 meter, has progressed. In addition to that functionality, it also now has the capability to deliver raw waveform data. And in some cases, that data can be streamed at 16,000 samples a second, 16 kilohertz. So a lot more information. And what's the value of this information is that applications leveraging analytics at the edge can now analyze that information, correlate that data, compress that data, and feed your digital twin or your analytics system or platform in the cloud. And that data can actually then let you reduce line losses, improve the quality of supply in your network, do targeted foliage management, extend the equipment, make sure you're not burning your transformers out too soon, and do preventative maintenance. And the last bullet is going to save hundreds of millions of dollars over the life of over the 20-year period. And it's actually going to help you really take the value of 2.0. And what's 2.0 mean? I mean, at the end of the day, it means more data. In 1.0, we were pushing about 60 kilobits a day. That's even at 5-minute interval channels, 3 or 4 channels, you're still at about 60 kilobytes a day. If you're actually sampling 16 kilohertz, that waveform data, and we know of applications that can take that data, analyze that data, compress it, you're going to get down to about 20 kilobytes a minute. So if you do that, you're going to be basically producing 28.8 megabytes of data per day from your AMI 2.0 meter. Now, if you don't want to watch that movie in 8K, you can watch it in 4K, maybe sample it at every 5 minutes, and you're down to 5.7 megs. If you want to sample it every 10 minutes, you can get lower. So what we're seeing is that it's really up to what fidelity do you want to see in your network, and you can then adjust that fidelity based on your requirements. The interesting thing about PLTE is that network, before I get there, I just want to kind of present, this. Sorry, I got a little bit ahead. But working with our partner Hubble, this is our view of an AMI 2.0 network infrastructure. You have the smart meter, the new 2.0 meter. You have the electric vehicle and its EV charging station. Now, Hubble has brought out kind of one of the first of its kind, I believe, integrated EV charger electric meter. In California, I know, the state I come from, they're pushing to have EV rates. In order to have the EV rate plan, the regulators say you must sub-meter that EV. So rather than having to put a second meter in a socket, you can now get an intelligent, smart EVSE charger, EVSE equipment, and actually get that billing information for that specific rate plan. And it's actually, if you want to see that product, it's over at the Hubble booth. So go over and check that out. And you know, Hubble also has a tremendous amount of line equipment. So now today, using either public or private LTE, not only can the line equipment and the meters, they can all talk together over LTE. And think about it, if you want to talk to someone on the other side of the world, you pull out your phone, you dial a number, you're talking to someone within seconds, right? You're going over cellular infrastructure, and you can then see these machines can actually do the same thing. So if you put intelligence in the devices, they can actually start communicating with each other, and they can make informed decisions. They can then also get information from the cloud and even make even more informed decisions from that digital twin representation. Just briefly, you know, this is just you know, kind of a geeky picture for how does it all work. But yesterday we were showing how 4 meters were communicating with each other and adjusting the appliances behind them or the chargers behind them. And so the communication kind of comes up over the radio access network, hits the core network, hits the gateway router, and actually then routes back to the meter. This all happens within milliseconds. And this could be on any device in your network, whether that device was in the same zone or it was hundreds of miles away. It's the same speed of communications. The other thing that PLTE lets you do is it actually lets you configure the channels, the data channels and the control signal channels to match your requirements and prioritize your data and your connectivity rates. So there's a lot of value that you can actually derive from a private network. I'm not going to go into this. This is some of the use cases that Dave will discuss. And at this point, thank you very much. I'd like to introduce Dr. Rieken.
Thank you, Ray. Oh, I'll need that. Yeah, so introduce myself. I'm David Rieken. I work for Hubble, which is, among other things, a metering company. I actually represent, or I lead an organization that is pretty unique in this industry. It's an applied research laboratory. My background before I came here was in defense. I used to work at, I've done research at MIT Lincoln Laboratory. I did research at Boeing's Phantom Works and General Dynamics. And about 2 decades ago, I made the change over to the utility industry. Why I did that is a long story and irrelevant, but I think it was the right thing to do. And really what we've tried to do in building this organization side Hubble is take that same rigor that you see at places like MIT Lincoln Laboratory and Phantom Works and build an applied research laboratory to solve these problems. And it's really the right time to do this because I'll take you back to the 1990s when I was an undergraduate at the University of Illinois. Very few people in electrical engineering were studying power systems at that time. And most of them who did, I'd say the most common things they studied were electric machinery, and they studied transmission networks. Distribution networks were just not studied. And if you go to any of the IEEE conferences, the academic conferences, and you talk to the people that are doing research in this field for decades, it was just transmission problems. All of the unsolved problems were considered in the transmission network. About 5 or 10 years ago, that changed, and all of a sudden these papers in distribution engineering started showing up again. And why is that? And it really goes back to how people like Thomas Edison, Nikola Tesla designed the distribution network in the first place. there's the distribution network was really meant to be kind of like just a giant surge suppressor. And it's premised on two, we'll say, axioms. One is that there's constant, plentiful supply of energy available at some central point, which we would call the substation. The second is, and then that the load is then also predictable. So predictability is one of those axioms, both on the supply and the demand side. The other is that each of the actors in this network do exactly one of those roles. They're either supply or demand. That is, the substation is always is supplying power, and the consumers are always consuming energy. Both of those have changed. Both of those axioms have fundamentally changed in just the last 5 years. You take a look at the continuing electrification of the auto industry, let's say. Basically, you look at from the perspective of somebody like me who works in distribution engineering. An electric vehicle is just a giant mobile battery with wheels that can plug in anywhere on the network. And so that predictability now goes away. It used to be that you have these curves that show exactly how much energy is being consumed, where and when. And power systems engineers, when they design a distribution network, they know exactly how big to make the transformers, and they know how to supply energy to them so that it's there when they need it. Among all of just electric vehicles are the most common, we'll say, the most pervasive of those, but everything, the electrification of everything has changed the demand curve. More severely, consumers do not act as demand actors only. They now can supply their own energy. And so you can get energy flowing back into the network. And this is not how the network was designed. The distribution network really has changed very, very little in the 100 years since Edison and Tesla designed it. And it was not designed to have energy get injected back into it. And so now we're to the point where prior to this, distribution engineering was considered a solved problem. It is now considered an unsolved problem. And it takes something like an applied research laboratory like Hubble has to investigate these problems, because we're seeing problems now that no one has solved before. And it's urgent that we get these solutions out. We've talked a lot about meter data. Ray's talking about, he's basically built a very large pipe that can bring back all of this data from the meter. Not too many people, though, we know, we know very well how to bring that data back. We don't exactly know what we would do with it when we get it. So I'm going to take a few minutes and show you what I think we would do with that data if you had this essentially infinite pipe that you can bring it back with. Since we are a meter company, and since we are a laboratory, we have the flexibility to do things like just plug in a meter. We did this in our laboratory. We took one of our electric meters, plugged it into a laboratory, and we wired it up so that we could actually gather that 16 kilohertz data out of the A to D converter. And we just let it run for a week. And I'm going to show you here what that data looks like. This is the top graph here. This is a time series plot over the course of a week that shows the voltage only for this 1 meter over the course of that entire week. The blue line is the voltage. The red line is the phase, because we're actually looking at the phasors here. So the voltage, really quick, the voltage is a 60 hertz sinusoid. If I just plotted that sinusoid out for you, it would be a boring plot. It would 60 times a second for a whole week, it would look like a blue bar. So what we do is we just isolate the magnitude and phase of that and plot those at each sample. Now, several things you can notice here. Over the course of a week, again, the blue line is magnitude. You can see how the voltage goes up during the day and down in the evening. And it does this periodically through the course of the day. That's because of the variations in load. Okay? You can also see simultaneous changes in phase over that whole period. That's completely expected. What I want to call your attention to, though, are areas where it deviates from that expectation. Now, I've heard soldiers who've been to war describe war as long periods of boredom punctuated by a few moments of sheer terror. And when I first saw this, that's the phrase that came to mind. I look at this signal, and I think it's long periods of boredom punctuated by a few moments of sheer terror. And I've highlighted 4 of these moments of sheer terror here, okay? You can kind of make them out. If you look in here, most of the time, again, remain conscious of the time scale here. You're looking at a signal over the course of a week, sampled at 16 kilohertz. Okay, so you cannot see these tiny variations. But if we just look at this July 26th, the second plot. Does this have a laser pointer on it? Let's see. Nope. Whoa. All right, we won't do that again. All right, so if you just look at July 26th here, you'll see that the magnitude is fine. Everything's fine. It's staying at a basically constant amplitude until for about 5 seconds, if even 5 seconds. The scale on this plot down here is 30 seconds. So just momentarily, that voltage dips down to 50 volts and then goes back up again. And then it happens again. You look at the next day, July 27th at 7:05 a.m. It happens, but it happens 3 times. Now, if you're no one would notice this. If you're a consumer, if you happen to live in the house that this meter supplies, you would not notice a 1 second dip in voltage. You might see a little variation in the lights. That's not uncommon, though, right? We've seen those. But it's not supposed to do that. The system, the distribution network is not supposed to do that. And this is not the kind of thing that most engineers worry about, or at least used to worry about. But it's not supposed to do that. That means something happened there that should not have happened. Now, what was it? We can't tell what it was from just this data. All you see is a single voltage drop there. But I want you to think about this. What if I had the ability to measure this signal, not just at this meter, but at the meter next door, the meter on a transformer adjacent to this? Let's just say I could look at it every single meter on that feeder. And if I could get that signal from July 27th and look at those three voltage dips, would I be able to infer what happened? And I'm going to make the argument to you that yes, I would. In fact, it would be a very simple thing for me to do. Now, as I said, this was in our laboratory, and since we are a research laboratory, we can hook a meter up. We had to take the glass off of it, we had to put probes on it, and we had to attach that to the A to D converter. It was a big mess to do something like that. We wanted to be able to see this on multiple feeders, so we built a device. This is a diagram of it. You can see a picture of it here. It's built to be installed by a utility. It fits in about an 18-inch weatherproof container, and it's meant to be mounted on the low voltage side of a distribution transformer. What we do is we connect with current transformers to both leg 1 and leg 2, and we connect that to a meter inside the box, one of our Hubble meters, and then we also connect the voltage up to the voltage leads on that meter. And then inside the box, we connect the meter to a Linux BeagleBone, basically a computer inside of that, and then we connect that to a 4G LTE Verizon cell modem. Now, what this does is it gives our engineers the ability to, through the Verizon cellular network, plug into that Linux BeagleBone and access the data that I showed you in the previous slide. So we go to our utility research partners, we ask them to install several of these devices on a single feeder, and then after we get them installed, our engineers can log into it and basically look at those signals that I was showing you on the previous page as if we were looking at signals in the lab. The difference is now we're looking at them on an actual utility. In fact, you could think of this as an early prototype of an AMI 2.0 smart meter, where you've got the meter inside of it. Here in the Linux BeagleBone motherboard and the 4G Verizon cellular modem are taking the place of, say, that eighth. Now, we went to one of our utility partners. We can only build a limited number of these. We build them all by hand. They're custom built in the laboratory. It's not a product. We don't sell it. It's research only. We built 10 of these and went to a research partner that was having problems on one of their feeders and asked them if they would just install 10 of these across that entire network. And then we set it in motion, and we watched it, and we waited for something to happen. And it wasn't long before we caught something. And I'm going to show you that here. In this plot, so here you'll see a line diagram of the feeder that we installed these on. You've got the substation over here on the far left, and it's there's a feeder coming out of it with 3 laterals. And 2 of those laterals have reclosers on them that I've identified R1 and R2. Everywhere where you see a circle here, and see something that says A1, E1, C1, anything like that, those are those sensors that I showed you on the previous slide. The first letter indicates the phase that it's installed on, because this is a 3-phase network, and the number is just a unique identifier. So sensor B1 is sitting right up here next to the substation on phase B, and it's basically, again, a meter with a Linux BeagleBone attached to it and a cell modem. Same thing, A1, C1, and then we've got several others on the lateral, on each of the laterals. Now, in this case, what you're seeing above these are line diagrams. These are the actual voltage waveforms, this time the complete sinusoid over a third of a second interval. And 3 things happened. 3 things happened during that 0.3 seconds. For the first tenth of a second, the system is in what we'll call steady state, or in equilibrium. It's functioning the way that it is ostensibly supposed to function. In the second tenth of a second, from 0.1 to 0.2 seconds, a fault has occurred. And we found out later through investigation of this, actually, that the fault occurred on phase A on that bottom lateral, not too far from the sensor there called A3. And when you look at that during that fault, by the way, you can see that over on sensor A3, the black line, the phase A plots are the black lines. You can see that the voltage went from about 240 volts RMS to something significantly less than that. And as you travel back up towards the substation, the amplitude on phase A during that interval also decreased, but not as much. That's because, of course, we're drawing a significant amount of current because of the short, and you're seeing actually the impedance of the line now play a role in that voltage reduction. Essentially, it's a voltage divider that has, during normal operation, the impedance of the line is so small that you can essentially approximate it to 0. The load has a significant impedance. In this voltage divider, the load impedance was 0, or very, very close to 0. So the voltage goes to virtually, you see a linear decrease in the voltage as you go to phase A. In the third regime, from 0.2 seconds to 0.3 seconds, that's where recloser R2 opens. It detects that current, the current inrush for 5 cycles. It opens, and when it does it, you see the voltage over on A3 go to 0 because, and by the way, the recloser, it's a 3-phase recloser, but it only opened on phase A. So the voltage there goes to 0. Everything else gets restored. You can see the voltage on A1 and A2 over here goes back up to 240 volts RMS. So basically, we're looking, if you look at this as a circuit analysis math problem, like the kind we did as undergrads, you're looking at 3 different circuits in here, and we have data for those 3 different circuits. Now, the problem for the utility, there's many problems that we could have. I think the most obvious one is, where was the fault, and what kind of a fault was it? And it's difficult to tell from these sinusoids alone what that is, but if we do some phasor math on this, if I go back and I just look at this and I just say, I just look at this as 3 different numbers. I'm going to say there's the before the fault, during the fault, and after the fault. And I want the steady state voltage and magnitude, voltage and angle, voltage, magnitude, and angle at each one of those regimes, then I can plot phasors in it. Now, looking at these line plots, it looks like the only change is on phase A. And I'm going to show you phasor plots now that happen after this. All right, so we go through and we do our mathematics. We come up with phasors on it. Because these are vectors now, we've plotted here as angles. Again, so here you see the 3 phasors for A1, B1, C1. The dotted line is before the fault, the solid line is during the fault, and the dashed line is after the fault. So those are your 3 different phasors. 2 things that I want you to notice here. First one is you can clearly see now the change in magnitude along phase A. That's to be expected. The surprising thing about this, and this is not something that we necessarily expected to see when we looked at this, is the angular change. You cannot see the angular change from those sinusoids, but when you look at the phasors, you can see it. And since this was a fault only on phase A, conventional wisdom, the conventional wisdom of the distribution engineering academic community was you would only see changes on phase A. But all of these circuits are coupled. And you actually see phase angle changes across the entire network. Look up at phase C, look at sensor C3. It's on a different lateral, a different phase. Yet its phase angle changes when the fault occurs. And this illustrates a fundamental precept of distribution engineering, is when no meter exists in isolation, essentially. When you make a change to a network, when a fault occurs anywhere in a network, that's a pretty dramatic change, but it doesn't have to be. Every time you flip on a light, you are making a change that is visible across the entire network. And this has led us to, within our research laboratory, basically to form a conjecture that we call the smart meter conjecture, which is that everything that happens on the distribution network can be observed by the smart meters, by signals like this. And then there's a corollary to that says, if you can get the data, if you can get that data from every one of those meters, then you can infer everything that happens on the network. So the point that I'm trying to make here is let's go back to that signal in the laboratory, the long moments of boredom punctuated by a few moments of sheer terror. And let's look again at that July 27th signal and think about it in terms of those phasers that I showed you. If you had that data from every single meter on the network, could you figure out what happened? Well, the answer is yes. It's actually quite easy. You can back out you take that data from every single meter, you plug it into your model for the network, and you basically solve an undergraduate circuit analysis problem. We call that state estimation, where you basically solve for the current and voltage across the entire network. That'll show you not just where the fault is, because it shows all of the current going to that fault. It'll show you how much current is flowing to it, so you can infer what kind of fault it is. You can back the waveform out. You can see what kind of fault that is. You can know exactly what caused it. If it's an intermittent fault, and these are the ones that utilities have the most problem with it. If it's an incipient intermittent fault that just keeps occurring and you can't back it out, this gives you the ability to do it. Basically, you've turned meters. Think of that if you took circuit analysis as an undergrad. In an undergraduate laboratory where your TA gave you a circuit board and an oscilloscope and said, apply Ohm's law to this by putting an oscilloscope at different points on it. It's the same problem, except here the circuit board is an entire distribution network and the oscilloscopes are every single meter. So, let me go right to this. So, there's basically, if we had this pipe available, there is nothing we could not do on the distribution network. But I see that happening in 4 steps. It's a big problem. You can't do it all in one step. The first step is just model estimation. And this is actually a bigger problem than it sounds like. When I talk to academics about this, they want to jump right to stage 4, really. And they begin with, like, if you're talking about state estimation, if you're measuring the circuit at every single point, if you don't know how the circuit is wired, you can't solve the problem. So model estimation is a way of verifying that. And this is actually an extremely expensive proposition for utilities. We work with one utility that has told us that they spent about $10 million to have someone manually go through their entire network, pole by pole, meter by meter, checking the wiring on them. It took them 18 months to do it. It was so long that by the time they were done doing it, the network had changed again. Why did the network change again? Well, every time a storm comes through a network or through a utility, their priority is to get the power back on as quick as they can. Linemen do not care which transformer the meter should be wired to. They care which transformer they can get it wired to the fastest. And after several storms, the topology changes. Our own informal surveying is that most utilities are about 85% accurate, which for back in the old days of distribution engineering was good enough. But when you're worried about reverse power flow and you're worried about solving the kinds of problems we're worried about, you need more like 99% availability. So this is where in the model estimation phase, you use this meter data to automatically figure out, without rolling trucks, what the wiring diagram of the network should look like. I'll tell you a little bit about how we do that. I'm going to talk about biology for a minute. I bet you guys didn't think you'd come here and listen to a computational biology talk, but I'm going to talk about DNA testing. If any of you have done 23andMe, you've already been a participant in the kind of mathematics that are being done to do model estimation. So I'll say my brother and I, our DNA is almost virtually the same. It's almost virtually the same because we have a common ancestor, a very recent common ancestor, our parents. But if I were to bring Ray back up here, and if he and I were to do the DNA testing, we would find that our genomes are separated by a little bit more. And if I were to bring my dog up here and do DNA testing on my dog, I'd find that his genome differs even more from mine, I hope. And then if I were to check it with a banana, and I would find it's even more distant than that. Why is it? It's because each of us has, as we continue this experiment, our most recent common ancestor goes farther and farther back. Now, biologists they've known about this for a long time, and they've used this to they can recreate the entire evolutionary tree by examining DNA from each individual species and putting it through these maximum likelihood estimators. They can figure out which specimens have the most recent common ancestors, and they can build the tree back from that. Now, what does this have to do with distribution engineering? Well, think back to that voltage waveform that I showed for a meter. If I show you the waveform for the meter that is right next to it, right next door to it on the same transformer, you would expect its voltage to be almost exactly the same. And why is that? Is because the only thing that's separating that meter for those two meters from each other is the little bit of conductor that they both have between the transformer, assuming they're on the same transformer. So unless the current through those wires is insanely high, consistently, those waveforms are going to look about the same. But as I move farther away from that meter, and if I go down the street, say I'll still be on the same phase, but I look at another meter and I look at its waveform, now it has more conductor between it. So there are more things that can go wrong. In this analogy, the transformers are ancestors. The wiring diagram is that ancestral diagram. And by doing this same kind of math that the computational biologists can do, we can back out how this network should be wired. And we have a prototype here for a software tool. If any of you want, stop over at the Hubble booth later. I'll give you a demonstration of it. But we have this working. We can reconstruct a network pretty much just from the voltage data from the meters using these computational biological techniques. That once you solve that model estimation problem, that opens up a Pandora's box of other applications that you can build on top of it. And I think all of this reduces to what is the most powerful one, which is that state estimation problem. If you have the correct wiring diagram and you have data from every one of the meters, voltage and current data from it, you can solve the circuit. And solving the circuit means you can figure out the voltage and current at every single point on the network under every condition. So certainly you can figure it out under steady state conditions. You can figure it out under faulted conditions, so you can locate where faults are. You can figure it out when there's reverse power flow. If you have, there's one customer that we have who has solar panels. They told me about this long feeder they have. They have a subdivision that is almost completely solar panels down at the end of it. And during peak solar time, they noticed that there's reverse power flow up that feeder about halfway to the feeder. I asked them, how did you figure that out? They said, well, we had to go out there manually and check it with a current stick. They basically they moved along the feeder until they found the point at which there was zero current. You can do this all automatically. If you have the voltage, just by taking the data that I showed you right there, all you need is the voltage and the two current datas from each meter. You combine that, you can figure out where there's reverse power flow. And if the data is coming back fast enough, as it would be with a pipe like this, then you can figure it out consistently. There is a problem in distribution engineering as we get to increase solar penetration. Say you've got a subdivision that's laid out like this. It's all solar panels. Every house on it has solar panels, we'll say. But over here you've got solar panels on phase A. Here you've got solar panels on phase B. And over here you have solar panels on phase C. If it's a bright, cloudless day, everything's fine. Everything's fine, assuming that you can manage the reverse power flow. Now let's put one cloud into this, and you just have one cloud that travels over the neighborhood like this. And so first it blocks out all the solar panels on phase A, then on phase B, then on phase C. What that does is it causes a pretty serious imbalance on the system. If the network was balanced before, it will not be while that's happening. Put multiple clouds into it, it becomes even more difficult. You can fix that, but you have to know how much power these solar panels are generating. So stage 2 is really taking that data, combining it with the model estimation, and doing circuit analysis so you can figure out how the state is. The next logical step then is really you jump from visibility to control. You say, all right, I can see what's happening with my network. That's great. I can see that it's bad. What do I do? What do I do with that? And Hubble actually happens to also be a distribution automation company. We sell things like capacitor banks and reclosers and voltage regulators. Let's talk about the capacitor bank problem for a second. Let's say I have 5 capacitor banks on a feeder. Right now, the way that works is each capacitor bank has a sensor at that point that's measuring the voltage and current just at that point. And it makes a decision about whether or not to flip on or off based on its local measurements on the grid. As we saw from one of the previous slides, when I turn on that capacitor bank, I don't just change the reactive power at that point. It changes across the entire network. And as long as the network is behaving predictably, that might be good enough. But with today's distribution systems, that's typically not enough. So if I have 5 capacitor banks on a network, let's say, and I want to decide whether or not they should be turned on and off, I really have 32 possible combinations, right? 2 to the 5th. I have the 32 possible combinations I can do. And if I know the state of the network now, then I can calculate for every one of those 32 possibilities which one gives me the most desirable outcome. So you're not now just doing capacitor bank switching based on local measurements, you're doing them based on overall global measurements. And you can get more precise control. You might even find you need fewer cap banks. You can add reclosers to that, you could add voltage regulators to that, and eventually you can add smart inverters to that. Smart inverters can be sources of reactive power, but being able to manipulate and control, basically set the phase. Right now the phase of an inverter is just set to match the phase that it's at, and you need a strong source in the network, what they call I forget what they call it, a guide source or a guide generator that has a high inertia, basically, so that it can follow that. You could get around that by having a control system in there. There's another problem in here. If you go back to where you have areas where you have very high reverse power flow, think about protection. I've talked to many protection engineers in many different utilities, and I always ask them, what are you guys going to do when the IBR penetration exceeds 5%? And by the way, our targets are to make it closer to something like 30%, maybe even 50% in some areas. What are you going to do? And they're like, we have no idea what's going to happen in there. The problem they're worried about is this thing called protective blindness. And I'm going to go back here a slide to where this thing tripped off right here. So remember there was a fault down here at A3. Suppose there was a significant amount of reverse energy flowing back into the network on A3. Then when a fault occurred at that point, it wouldn't just draw current from the substation, it would draw it from those distributed generation sources downstream. And it could potentially reduce the current flow from the substation through R2 to the point where R2 would not flip off. That creates a significant problem for it because it's a safety hazard. If you're tracking state, if you're following the state and you know how much the current is flowing, you know how much generation is coming from those distributed generators downstream, then you can adaptively change the settings on those reclosers. Basically, you can adjust the settings on those reclosers continuously so that if a fault occurs at any time, the recloser is ready to do it. This could potentially get us above that 5% penetration. Right now, utilities, I don't know if you guys know this, but they're going to cap IBR penetration at 5%. They will reach a point, if more than 5% of your neighbors have solar panels, you will not be allowed to have them on your network. So that's what I see as phase 3, is being able to do what we call responsive automation. The final step, then, is let's take it a step further. So now we have a completely integrated system. All of this data from the meters is being used to constantly monitor power. We're responsively changing our automation equipment to adapt to conditions on it, so it's basically autonomous at this point. Let's go a step further and say, if I know what the network looks like now, and I've been studying it for a very long time, in some cases years, I can predict what that state will be 5 seconds from now, 15 seconds from now, 5 minutes from now. I can basically say, I can come up with a model for every single element on the network. You get into a little bit of artificial intelligence here, deep learning in particular, where you come up with models for all of these individual components, but then you can predict with varying levels of probability what the network will be doing at some point in the future. And you combine that with your automation, and you can say, now I know that the state looks like this right now. 15 seconds from now, it's going to look like this. I can change my automation equipment before those conditions happen. I can run all these automation algorithms and say, this is what I want the network to be doing at that point. And you could, at this point, you're essentially talking about preventing problems that have yet to occur. And this, I think, is the holy grail of distribution engineering, because at this point, you're not just responding to problems, you're not just responding to outages, you're preventing outages from happening. So, one last thing. When I talk to academics about this, about state estimation in particular in networks, they say if you're not going to be doing it, they're so used. By the way, this kind of thing started in the transmission network. If any of you were in the blackout of 2003, I was actually. I lived in Ann Arbor, Michigan at the time. That blackout was caused by a phase imbalance, or actually it wasn't caused by the phase imbalance, but it could have been prevented if they had been examining the phase between these two different transmission interconnects. Particularly, there was a massive phase imbalance between Western Michigan and Ohio in the seconds leading up to this. And if they had seen that, they would have been able to prevent it. And so at that point, that's when transmission engineers came up with the idea of phaser measurement units. And you'll notice we haven't had a blackout like that since, right? And the algorithms that they came up to do this with, they basically run fiber to every one of these PMUs, and they stream data back at something crazy, 30 kilohertz or higher. And so when I first started talking to academics about how we could use phaser measurement units as meters in the distribution network, what they said was, well, if you're not going to do it at those speeds, basically 30 kilohertz, you're not going to be able to get any value out of it. But there's actually, and that's true. And if you look, so what this plot shows here is how frequently you get data from the meters on the horizontal axis, and you get with the amount of data or the frequency of the data increasing as you go to the right. And each of these are the different applications that you can do at those points. And so if you go all the way over, so where you have 30, like we'll say 30 hertz is typical for phaser measurement units, that's where you can do real system stability analysis, island detection, and those kinds of things, which are really problems that are not the problems that utilities are facing on the distribution side right now. We have a system right now, we're measuring the state about once per day. And once per day, there's a lot you can do with that, it turns out. You can do, that's the connectivity estimation, impedance estimation. We can locate IBRs. So there's this whole continuum. As you increase the frequency of the data, you move farther to right to left, you start to get more of these applications in place. And so really, as we move down this line here from 1 to 4, going all the way to predictive estimation, we find ourselves moving down that line. This is really what I think this is huge. Being able to collect massive amounts of meters, there's a lot of information there. And basically every problem in distribution engineering reduces to a problem in state estimation, which can be solved really very easily just by proper application of that data. I'll go ahead and stop there. I don't know if anybody has any questions or what the plans are here, but yeah. Questions?